Hello, Dragons. This is the video that you need for section 12.1. And what we'll do in section 12.1 is we're going to go over the basics of three-dimensional figures. So on this front page of your slides, you have some basic definitions, some things that we need to know going forward. The key is a polyhedron. A polyhedron is a solid that is bound by polygons. And so I'm going to highlight this word right here, polygons. This is the key to your definition. Polyhedron is a solid bounded by polygons that enclose a single region in space. Now, there's some other terms that you need to know: a face, edge, and a vertex. But I want to go a little bit deeper with each of these terms here. An edge. An edge is a segment. It's a line segment that is the intersection of two faces. Now, this top face up here that's colored, this is what we're going to call one of the bases. And so this little line segment right here is an edge. It's correct. It's calling it edge, but it's more specifically called a base edge. And so what we need to do is add some adjectives to our knowledge there. That's a base edge. Now, this edge, where it actually says the word edge right here, that is an actual edge, but that's on the lateral faces of the figure. And so this would be more accurate to call it a lateral edge. And so when you see that term in the future, base edge and lateral edge, we'll assume that you know what that means. And so just keep that in mind. The faces, those are just the sides of the figure. And the vertex, those are just the points where line segments meet or when three or more faces intersect. Okay, on the next page are some basics of polyhedron and things that are not polyhedron. And so our definition of polyhedron again is it is a figure that is composed of polygons. And so if we come down here to these not polyhedron, a cylinder is not a polyhedron because the bases are circles, and circles are not polygons. The edges are not straight, and so that's why cylinders, cones, and spheres are not polyhedron. And so, prisms and pyramids, all of the faces of a prism or a pyramid, those are all polyhedron, or those are all polygons. And so we got to keep that in mind. Also on the side, this is real kind of easy to miss. I'm going to kind of circle it here. It says polyhedra. They are named by their base. And so basically what I've got for you is down here at the bottom, I have just a bunch of diagrams that show you how do you name a prism or how do you name a pyramid. Again, you just name it by its base. If it's got a base of a pentagon, like this last one right here, it's going to be a pentagonal pyramid. So again, that's more basics that we need to know as we proceed throughout the unit. Okay, the next slide are platonic solids. This is a special type of polyhedron. And so I know some of you like to hear the big grand scheme of things here. And so I'm going to draw you a quick Venn diagram here. And so if we were to say in this Venn diagram, all of our polyhedra, wow, I just totally messed that up. So let me respell that. So polyhedra. So all of our special polyhedra make up this Venn diagram. Well, there's a smaller little circle inside of the Venn diagram, and these are what are called the platonic solids. Platonic solids, they're special in one way, and I'll reveal the box for you here. Platonic solids are regular polyhedron. What that means is all of the faces are congruent to each other. And so if you look at this regular tetrahedron over here, this has got four faces. Well, the four faces are all equilateral triangles. And so basically you can just tell yourself this is four equilateral triangles. Those make up all of the faces. A cube, those are made up of six squares. All the squares are the same. And then that's going to be the same for all of the rest of the platonic solids. The octahedron is made up of 8 equilateral triangles. This regular dodecahedron, that's kind of the oddball. That one's made up of 12 regular pentagons. And then the icosahedron, that's a big 20-sided figure, and that's made up of 20 equilateral triangles. And so that's what a platonic solid is. All of the faces are congruent polygons. All right. So basically, going forward, you just need to kind of know the basics of platonic solids, what they are, what they're made up of, and you need to know their names too: tetrahedron, octahedron, cube, etc. And so just keep that in mind. Now, this is the really difficult part of the lesson and its cross sections. The reason why it's difficult is there's a lot of information, first of all, but there's also a big it's a big test of your visualization skills. How well can you see the cross sections here? So your official definition of a cross section is that it is a two-dimensional figure, and it is formed when a plane slices or intersects a solid. And so if you look at the diagram here, we have this big blue plane, and it's kind of slicing through this cube, and then the cross section is this little triangular region. That's the intersection of the plane and the solid. And so here, when a plane kind of intersects this cylinder, it's going to create this circular cross section here. And so what we're going to do is on the next few pages, just kind of go over some of the notes, the basics of the notes. I'm not going to read all of it to you, just kind of hit the high points and kind of explain what we need to know going forward. Okay, on the next page, the next two pages, these are the common cross sections of prisms and cylinders. And I'm just going to kind of scroll back and forth here. These are the common cross sections of pyramids and cones. Now, bottom line is that you just kind of need to know the basics here. And we're only going to concern ourselves with the cross sections that are parallel to the bases or cross sections that are perpendicular to the bases. We're not going to go too deep on this. However, I do have some animations here to kind of help you all see this here. So let's keep prisms and cylinders in mind, and we'll come back to this slide here in just a moment. All right, so let me go to this animation here. And so what I have is a triangular prism, and I have a cross section that is this light blue plane. And I'm just going to kind of scroll this down a little bit. So as I move the plane up and down, notice the cross section's height also changes. And if I go above, the plane is above the figure, it does not intersect it, so there's no cross section. So when the plane actually intersects the solid, it creates a cross section here. All right, so here's my cross section, and I'm just going to kind of play around with this a little bit here and let you see the animation here. As we go, we rotate our plane. All right, look what happens as we make this thing kind of go diagonal. We're going to rotate it toward vertical here. This is still a triangular cross section. And this is kind of weird. This is going to be a tough visualization for some to see, but this might help you kind of see it from this point on. It's weird that when you do a diagonal cross section, you actually can get a trapezoid in this case. And again, I'm not going to ask you all to know these weird diagonal cross sections. That's beyond what we need to know for the course. But again, it's just kind of an interesting visualization there. You can actually get a trapezoid cross section. When you do that. But let's just work our way to the vertical cross section. That is perpendicular to the base, and that's going to give us a rectangular cross section. And so I'm just going to go back to our notes here. That's why this is the results of the what I just showed you there. If you have a parallel cross section, whatever it is, it's going to be the same shape as the base. Now, if you are going perpendicular to the bases inside of a prism, you have to have a rectangle of some kind. And so I just need you to kind of keep that in mind going forward. So now let's come down to cylinders and take a look at these. We should have a circular cross section and a rectangular cross section. And so let me go back to my animation here. Let's go to cylinders. And so we'll do the same thing. We'll kind of play around with this a little bit. Here's my cross section. And it's now the plane is below the cylinder, so there's no cross section. Here's my cross section. And so I'm just going to kind of let you see that the cross section is a cylinder. And what we'll do is we will rotate the plane horizontal. Now, this is interesting. This is one of the weird visualizations of the course is that this is an oval. It's what's called an ellipse. And so when you go diagonal to the cross section, or when you make your cross section when the plane is diagonal to the base, it's actually going to create an ellipse. And then this shape, oh my gosh, this one's really strange. Think of it as a rectangle. The top sides on the bases, those are straight, but then the edges, the left and right sides, those are not straight. Those are curvy. Those are actually the sides of an ellipse. And so it's kind of a rectangle and ellipse combined. And then as we get vertical here, that shows us that when we go perpendicular to the base, the cross section has to be a rectangle. All right, so there is kind of the visualization, so you can kind of see the cross sections, the common cross sections of the prisms and cylinders. And again, let's just focus on the parallel and perpendicular cross sections. Let's not worry about those crazy shapes that I showed you a moment ago. All right, if we move on to pyramids and cones, we'll go a little bit quicker here. These demonstrations here, what I need you to see is the commonality here. This little green shape in my notes is a rectangle, and notice that the pyramid itself, its base is a rectangle. You're going to get the same shape as the base, and that's going to be true here for the cone as well. And so when you all do looking for patterns on this, if you ever have a parallel cross section, just remember it's got to be the same shape as the base. Now, it's not going to necessarily be the same size. It'll be similar to the base in terms of its dimensions, but it's going to be the same shape. What's different is when we get to pyramids and cones, when we get to the perpendicular cross section to the base. All right, and so these are going to give us triangles on both of these shapes. And so I want to kind of go to that and let you kind of see it here. So let's go to the rectangular pyramid, kind of like what was on our notes. And so here is our rectangular cross section when I go or parallel to the base. And when I start rotating, again, there's kind of another trapezoid thing when we go diagonal to do a diagonal cross section. And what I've got here is I made that go completely vertical. I'm going to have to move this just a little bit so that it gets to the vertex. All right, so if we have a perpendicular cross section and it goes through the vertex, then we're going to get a triangle. Now, notice what I did there. I moved this just because it's perpendicular to the base. You're not always going to get a triangle. It has to go through the vertex of the pyramid. And so this would be a trapezoid answer. It's perpendicular to the base, but not through the vertex. And so just kind of keep that in mind. I'm just trying to go over the simple things on your notes there. Notice on our notes here that the cross section does go through the vertex. So that's why it's going to give us a triangle there. Let's go ahead and finish the last one here. Let's go to the cone. And let me just let you see that one here. And so let's rotate the plane horizontal. Again, the diagonal cross section is going to give you an ellipse. Oh, yikes. That one's kind of strange. It's an ellipse, but the kind of half of ellipse, if you want to think of it that way. And then when we go vertical, there's going to be our triangular cross section there. And if some of you want to kind of see this there, if we kind of move it, again, it's kind of an elliptical curve, but then the bottom part of that shape is a line segment. And so, again, we're going to make sure that our cross section does go through the vertex. That's what we're going to need to know for our notes. So that takes care of the next two pages of our notes, the common cross sections, and then you kind of maybe see some of those cross sections in action there. All right, the next cross sections you need to know are what's called conic sections. And so when you get to Algebra 2 and pre-calculus, you're going to learn what are called conic sections. And I'm going to kind of type this out here. Conic sections. And so you're going to go over all of the much greater details, like what's the equation of a parabola? How do you find the eccentricity of an ellipse? I mean, there's so many details and so many wonderful things that you're going to learn about the conic sections. What you're going to need to know for today and for this unit is not necessarily all the details. You just need to know how are the cross sections formed. All right. And so what I've got for you down here, I've revealed the notes for you here. These are how you'll create the cross section. So you just need to know the names: hyperbola, circle, ellipse, and parabola, and know how they're formed. We're not going to go much deeper than that. And I do have another animation here for you all to see. And this is the conic sections here. Real quick before I almost forgot this here. When you do conic sections here, I'm going to highlight this on your notes here. The following figure, I'm going to read this to you. The following pictures displays the cross sections of conics. The figures below are what are called double napped cones. Basically, that is just two cones this top cone and this bottom cone, and they are joined together at their vertices. And so they share a vertex, and then the bases are going to be parallel to each other. So basically, it's just two cones stuck together at their vertex, but the bases have to be parallel. And so when you have a double nap cone and you start doing cross sections of a double nap cone, you're going to get these special conic sections. And so now let me go back to the visualization here and the animation. So what I've got here is a plane. It's a blue plane, and it is parallel to the bases. And what that does is it creates this cross section here in orange, and that's the circular cross section. And so on your notes, we wrote down how do we form a circular cross section by having a plane that's parallel to the bases. All right, so that's where this circular cross section comes from. And now what I'm going to do is going to play the animation and kind of stop this here. What we're going to do is we're going to rotate this plane to vertical, kind of like what I've been showing you on the other um, shapes, and kind of show you some of the cross sections here. All right, so I'm going to play this, and we're going to kind of stop right there. And so we went. We're not parallel to the bases anymore. We're diagonal to the bases, and so that's a new term called oblique. Oblique, oblique. That just basically means diagonal, non vertical, non horizontal. And so this plane is oblique. It's diagonal to the bases. And what that's going to do is it's going to stretch the circle out into an ellipse. And so the key to this is, though, that if you look at the blue plane, it's above the base of the circle, the bottom, it's above the base of the bottom cone. And so this blue plane does not intersect the base. And so when we come down here to my definition, it is the ellipse is formed by an oblique plane that does not intersect a base. And I'm going to go back to the demonstration here. That blue plane does not touch the base. All right, so let's keep going here. This thing's going to keep rotating. And now look what happens when it touches the base. So now the blue plane touches the bottom base. Now it doesn't touch the top one, it kind of goes below it a little bit. But now the blue plane is touching the bottom base, and it does not create an ellipse anymore. It creates what's called a parabola. And so, again, that's another oblique plane. It's a non horizontal, non vertical plane, but it's touching a base this time, and that creates our parabola. And if we keep going, and eventually, right here. All right, right here is when the plane, the blue plane, is going to touch both bases. Now, it could be oblique, it could be vertical, it doesn't matter. But the key is on our notes, and I think I'm going to go back to this here and let you all see this. A hyperbola is formed when the plane intersects both bases. It could be perpendicular, it doesn't have to be, but it just has to touch both bases. And if you take a look at these white curves, I've got these white curves here. I'm going to kind of scroll over this with my mouse. These white curves make up what's called a hyperbola. A hyperbola is a singular word. Hyperbola is just, there's no S on it. It's singular, but strangely enough, it's made up of two curves. All right, so the two curves make up a singular object. And so that is our hyperbola. And so that's basically how and why these things are the way they are. So just know, how do we create these cross sections? And again, you'll go in much greater detail of all of these shapes when you get to your Algebra 2 and your pre-calculus classes. Okay, on the next page, we have a cross section of a sphere. Let's knock that one out. That one is going to go real quick and real easy here. So let me go to cross sections of a sphere. And basically, this one's easy. No matter how you slice through a sphere, you're always going to get a circle. I'm just going to kind of rotate around. It does not matter. It makes zero difference how you slice through a sphere. You're going to get a circle of some kind. Now, they're going to be different sized circles, different sizes, different all that, but it's going to be circles. Now, there's one exception to this, and I'm going to move this here above the sphere, but right here, when I touch just the very, 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 very tip of the sphere, that's going to give me a point. And so that's kind of a special case there. If the plane is tangent to the sphere, then you'll get a point cross section. Otherwise, it's got to be a circle. So just remember that it's either a circle or that special case as a point. And so when you fill in your notes, you'll just say points. So let me go ahead and write that out. So you can either get a point. That one's the uncommon one, but most specifically, you'll get a circle. More commonly, you'll get a circle. Okay, now the cross section of a cube. These are a little bit harder to visualize here. And here are all of the common cross sections. I mean, I got 6 blanks, and there's actually should be 7. There's 7 possible cross sections, and you don't need to be able to recreate these. You don't have to be able to um, draw them or anything like that. But we need to know that these are possible. And so what I'll do is another demonstration to kind of let you all see the common cross sections. And so your common cross sections are a rectangle and a square. You could get all types of triangles. The scalene, isosceles, or equilaterals. We'll just say triangle generically. You can also get trapezoids, parallelograms, pentagons, and hexagons. And some of you will be able to see, oh, I can see the square cross section. I can see the rectangle cross section. Most of us will be able to see a decent amount of these. Those make sense to us, but it might be hard for some of us to visualize or see the pentagon or the hexagon cross section. And so I do have another um, demonstration here. So let me go to cross sections of a cube. And so let me just kind of let you all see some of these and why they are the way they are here. All right, so what I've got here on the opening part of my modeling here is a square cross section. And so I'm just going to kind of move the plane up and down. It doesn't matter where this plane is. As long as it's parallel to one of the bases, it's going to give me a square. So that's the easy one there, square. Let's go ahead and go to rectangle. What I'm going to do is I'm going to do some tilting here, and I'm going to tilt that up, and I'm going to turn my plane just a little bit here. All right, so what I've got here is I'm going to just go corner to corner, and if I rotate my cross section or rotate my plane, I'm going to get a cross section like this that'll give me a rectangle. So that is a way that we can see the rectangle. Now, from the rectangle, I think it'd be easier for me to show you the hexagon cross section, and it actually you might see it a little bit better once you see this. So focus on this rectangular cross section, and I'm going to tilt the plane just a little bit and let you kind of see. Look what happens to that rectangle. You see, I'm tilting the plane. It's oblique now, but look what happened. It kind of slices through the cube, and it forms this weird hexagon. All right, so you could get a hexagon um, basically from the rectangle cross section if you kind of rotate it your plane a little bit. All right, so let's try the pentagon here. Let me see if I can show you this one here. And let me move my shapes a little bit right there. Okay, and let's try that. Let me get. All right, so take a look at this odd figure here. This is a pentagon, and if we count our sides here, this top side, I'm going to put my mouse over this. This is one side, so that's 1. This little small length is 2. From here down to the bottom corner is 3. From up here is 4, and then this little small length is 5. So there's your pentagon. Not the usual pentagon that you all are used to seeing, but that is a pentagon there. All right, so let's kind of try some more of these here. I think some of you would want to see maybe the triangle. And let me kind of play with this a little bit here. Let me go down. And let me kind of move this up a little bit. And I will get there eventually. So if we do a triangle, let's try. I'll come up with one here in a matter of time. There we go. All right, so there's a triangular cross section right there, and again, the plane is diagonal to, or it's oblique to the bases, and so it's kind of slicing through at a diagonal. So there is a triangle possibility there, and let's try a few more. And let me. This is just a normal quadrilateral. I mean, you could get a run-of-the-mill plain quadrilateral, and it won't be too exciting there. This would be a fair example of a parallelogram. All right, and so I know I put that on the notes. Here's a fair example of a parallelogram. And I think the last one I need to show you is a trapezoid. And so let me try this. There we go. I think that's it right there. All right. And so there would be a trapezoidal cross section. And so, again, you don't need to be able to recreate this. You don't need to be able to draw this. I mean, even visualizing it may not be necessary. All you just need to know are the possibilities. What's possible? The possible cross sections in here they are. And so, rectangle, square, all types of triangles, parallelogram, pentagon, hexagon, or a trapezoid. Okay, and so on the next page are just a battery of just simple test level questions. It's that simple. I give you a cross section or give you a diagram, and I say, what's the cross section? And so for the answers, the triangular cross section, that's this red object right here. The circular cross section, this little red object that I'm coloring here. The hexagon is going to be this little. I miscolored that. That's this little area here. And then the triangular cross section. Yeah, I'm not really coloring that well, but we'll have to get over that. But there's your triangular cross section there. So these are basic test questions. You just need to be able to tell me what are the common cross sections here. I'm not going to go through the notes on every single one of these 9 always, sometimes, never questions. I'll leave these up here for you all to practice and just try those. Just use your basic notes. To answer those. If you have any questions, you can talk to me or Coach Athens in your video conference. Okay, now we're going to get to the nitty gritty here. These are the challenging questions of cross sections. What we're going to need to do is to be able to, now that we know what the cross sections are, what's possible, we need to be able to use it. And so we're going to use some old knowledge that we've learned in the past on solving some of these questions here. All right, so let's tackle number 1. It says determine the area of the cube's cross section if each side of the cube is 4 centimeters long. And so the answer to this question will be 8 root 3, and we'll go over where we get that here in a moment. It's 8 root 3 square centimeters. And so there's a couple of things that have to happen on this. The cross section, we know that this is a triangular cross section here. And the key to this is understanding what kind of triangle is it. On our notes, all triangles are possible, equilateral, isosceles, or scalene. And depending on what kind of triangle it is, it'll determine how easy or hard the question is. All right. So, first things first, think about it. Take a moment and ask yourself, what kind of triangle is that? That triangle is equilateral. All right. And so let's go over why it's equilateral right now. So this is a cube. By definition, all sides of a cube have to be the same. So let's just put 4s in all locations there. Now I'm going to highlight a triangle here in red. Now we don't know any of the sides of our cross section, but we do know some things here. And so what I'm going to do is I'm going to highlight in red this little triangle. Now, this triangle is on the face of the cube. And since one side is 4, all of the sides are 4. And this triangle is a right triangle because cubes have to form squares and those form right angles with each other. So we can reasonably assume that that red triangle is an isosceles right triangle. And we learned about that in Unit 8. That's a 45, 45, 90 triangle. So that means my cross section, and I'm going to draw the cross section a little bit bigger off to the side. Here's my equilateral triangle, and I'm going to color. I'm going to do a little bit of color matching here. This little red side right here, the hypotenuse of my triangle, I'm going to color that right here. So I know that that length has to be 4 times the square root of 2. All right. And we can do the same thing. We can do 45, 45, 90s to find the other sides of this, but it doesn't matter. It's unnecessary. All the sides of the equilateral triangle are 4 root 2. So I will propose that you all use the equilateral triangle formula, which is s squared root 3 over 4. And so we're just going to need to plug in our 4 root 2 into the formula. That's a bad 4. All right, so 4 root 2 squared times the square root of 3. Let me type the right thing down there. So 4 times the square root of 2 quantity squared times the square root of 3 divided by 4. All right, so what we need to do is evaluate 4 root 2 squared. And so if you want to get your calculators, do this with me. 4 squared is 16. 16 times 2 is 32. And so that means this is going to be 32 times the square root of 3 over 4. And if we simplify the fraction, that's going to give us our 8 root 3 square centimeters. And so what you're going to need to know on this question is, just to kind of summarize it, you needed your special right triangles you learned back in Unit 8, and then you had to combine that with the equilateral triangle formula that you learned back in Unit 11. All right, so that's going to take care of that that cross-section question for number 1. All right, let's move on to number 2. It says determine the exact area of the cross-section. It says the cross-section distance to the center is 2 root 3 meters. The radius of the cross-section is 2 meters. We need to find two things. We need the area of the cross-section and the radius of the sphere. Now, we learned back a few moments ago that the cross-section of a sphere is always a circle. All right, and so what we need to do is, let's just answer the question real simply here. 4 pi square meters is the answer to the first bulleted question. The way that we're going to find that is with pi r squared. So area is equal to pi r squared. And we're just going to plug in the radius. It says the radius, the area of the cross-section is what I want. Well, I give you the radius of the cross-section. And so this is going to be pi times 2 squared. 2 squared is 4, and that's how we get our 4 pi answer for the first bullet. Now, here's the challenging part. This is the part that would concern your teacher the most. This is what you need to really drill into your head. This is the important part. Finding the radius of the sphere. Now, here's what we need you to know. Within every single sphere, and I'm going to draw this for you. I'm going to just circle, I'm going to draw this in. Let's go orange here. There is always going to be a right triangle with regards to the sphere and the cross-section and all this. And so I want you all to follow with me here. From the center of the sphere, let's draw a line all the way to the center of the cross-section. All right, so that is going to be one of my lengths of my right triangle. Let's draw a radius from the center of the cross-section to the edge of the sphere. So that is the radius of the cross-section. And then let's draw our hypotenuse. The hypotenuse is going to go from the center of the circle, the center of the sphere, all the way to the edge of the sphere. And so what I've got there in orange, I've got a special triangle, and I need you to add this to your notes and know this going forward. I'm going to blow this up and let's formalize this here. The hypotenuse is the radius, and so we'll say the R, and this will be of the sphere. All right, so the hypotenuse of this right triangle will always be the radius of the sphere. Always, always, always. So please put your radius of the sphere as the hypotenuse. Now, this vertical distance, this is from the center of the sphere to the center of the cross-section. So this is a distance. And so we'll just say this is the distance to the cross-section. So I'll just say distance to cross. All right, and so the top length up here is the radius of the cross-section. So let me go ahead and write this down. This is the radius of the cross. So the radius of the cross-section. So there's your 3 legs of, or there's 3 sides of the right triangle. This is going to show up in every single sphere cross-section question, and this is the only chance you have of solving these problems correctly. So you have to know this right triangle. So the legs are the distance to the cross-section and the radius of the cross-section, and the hypotenuse is always going to be the radius of the sphere. All right, and so now I'm going to kind of clear this out a little bit because we're kind of running out of room here. So I'm going to just clear out all of my writing, and let's solve the problem now. Now that you've seen the basics, now let's see if we can use this to execute the problem here. So it says the cross-section distance to the center is 2 root 3. And so what we need to do is make sure we put that in the correct spot. The 2 root 3 counts as a distance. So that's that vertical length there. The radius of the cross-section is 2. Now, I know some of you will recognize this as a 30, 60, 90 triangle. and it is in this case only. Don't assume that all of these are 30, 60, 90s. It just happened to work out here that it was 30, 60, 90, not always. And so let's just go Pythagorean theorem on this. Just get in the habit of doing Pythagorean theorem and don't assume 30, 60, 90s. This one, it just happened to work out to be that way, but it won't be going forward. All right, so go Pythagorean theorem. And so we have r squared is equal to 2 squared plus 2 root 3 squared. And if we simplify this, 2 squared is 4. And if we square the 2 and the root 3, we get 12. And so r squared is equal to 4 plus 12, which means that r squared is 16. And so that means the radius of the sphere has to be 4, which is where that answer that I advertised came from on that. All right, so what I'd like you all to do for me is this. On this page from question 2B and on the next one are a battery of questions. It is going to be doing the exact same thing. So take a few moments and practice those for me, and we'll go over a few more of these here in just a bit. Okay, so you've had a chance to practice. If you had troubles, issues with that, let's go ahead and knock these out. And let's clean these up here. So we have a right triangle inside of our sphere. And it says the cross-section distance is 8. So that means the vertical distance is 8. The radius of the sphere is the square root of 65. And it says we need to find the radius of the cross-section. So if we do Pythagorean theorem, r squared plus 8 squared is equal to the square root of 65, that squared. And so if you do Pythagorean theorem correctly, you should have r squared plus 64 is equal to 65. And if you subtract 64 from both sides, you're going to get r squared is equal to 1. And then once you know the radius of the cross section, you know it's 1, and then you can plug that into the area formula. Pi r squared is just going to give you pi square centimeters. And so that's how you do question 2B. If you had troubles with number 3, here we go. Let's do the same thing. We have our right triangle, and let's fill in what we know. It says calculate the area of the sphere's cross section if the sphere's radius is 13. So that means we put the 13 on the hypotenuse. The cross section is 5 units from the center. That's the distance. That's the vertical length. And so you'll do Pythagorean theorem again. And so what we'll need to do is, and I'm going to go a little bit quicker on this, Pythagorean theorem, you should get 12 when you do that. That'll be r squared plus 5 squared is equal to 13 squared. If you solve this Pythagorean theorem formula out, you should get 12. And now that you know that the radius of the cross section is 12, now you can throw that into the area formula. If you square 12, that's where this 144 business is coming from. So 144 pi square units is what we're looking for, number 3. All right, the last one, number 4, it says deduce the radius of the sphere if the cross section's area is 400 pi. All right, so now we're going to have to tap on the brakes here. So the area is pi r squared, and they give you the area of 400 pi. And so you're going to have to work backwards to find your radius. And so if you divide both sides by pi, you get 400 is equal to r squared, and you take the square root of 400, that should give you an r of 20. So we know the radius of our cross section is 20, and now we can start to get the ball rolling on our problem. The radius of the cross section is 20, so let's put that on the top. 15 is the distance to the center, so let's put that as our vertical length. And we need to find the radius of the sphere, so that'll be the hypotenuse. And so this will be r squared, r squared is equal to, so let me erase that. I almost made a mistake. So r squared is equal to, and that will be 15 squared plus 20 squared. And if you crank this out on your calculator, you should get r squared is equal to 625. And if you take the square root of that number, the square root of 625 is 25. All right, so that takes care of kind of the cross-section questions, and we're done with kind of the horrible things there. What we need to do is kind of go on to looking at isometric and orthographic views. And so what these are just drawings, and you could be asked like on a test or a quiz just to kind of like a multiple choice. What's the front view, or what's the back view, or top view? And so we just kind of need to maybe see this and be reminded of it if you need to. And I'm not going to go over all 6 views. I just want to hit the high points here. Now, notice on this first question, it says the front. So that's the view from this perspective. And so if that's the front, this is the right side, and then over here will be the left. All right, so if we look at the thing from the front and the front only, instead of a three-dimensional object, we should just be seeing two squares. All right, so we should just be seeing two squares there. If we look at it from the very, very top, if we just look over the thing, we should be seeing four squares. And then if we were to look at it from the right, we should be looking at it from the right. We should be getting two squares there. All right, so let's just do a couple more of these. Let's just do some quick views there. If we look at this figure from the front, we should have on the left side of our diagram, it should be two squares stacked on top of each other like that. And then there should be a single one next to it. So that's going to be my front view. If we look at the thing from the very, very top, we can't see any depth on this. And so all we'll see from the top is four squares. We can't see the stack, but we'll see four squares. And then if we look at it from the right, I'm just going to say this is right here. If we look at it from the right side, what you'll see is something that looks like this. All right. If we look at it from the left, it'll be kind of the reverse. It'll look something like that. All right, so there's just some examples on how to do some orthographic views and so orthographic drawings. On the next page here are some multiple choice questions. These are just some examples, some test level questions that I could ask you to do here. So maybe just practice this, take a look at these. I've got the answers up here for you to look at when you're ready. And then we're going to move on to nets. All right. So what we're going to do with nets is that we're just going to practice our identification here. A net is it's a two-dimensional representation of a 3D solid. Basically, what you're going to do is you're just going to take a 3D solid and you're just going to unfold it into a two-dimensional object here. So what I've got here for you is the types of test questions that you'll see. I'm going to give you a net, like let's say this one right here, and I ask you, okay, if you folded this thing up and made a three-dimensional solid, what object would it be? In this case, it's a pentagonal pyramid. And so what we need to do is get comfortable with how do we recognize what the three-dimensional object is here. And so I've got some good examples up here, but I also want to just kind of go over maybe some patterns, some things that'll help you going forward here. You don't have to turn back in your notes on this, but I do want to kind of go back to it here just a little bit here. When we did back on this I think the second page here, when we did polyhedron, a prism. Now, if you take a look at this prism here, it says it's a polyhedron with two congruent faces connected by parallelogram faces. Well, typically, when you have a prism, the faces will typically be rectangles. And when you go to a pyramid, the lateral faces, those will be triangles. And so I just want you to keep this in mind. If you see a bunch of rectangles, it's going to be a prism of some kind. If you see a ton of triangles, like a lot of them, then it's more than likely going to be a pyramid. That's a good place to start when you do these types of problems. And so now let's go back to our nets here. And so what we have here is we have one triangle. So here's a triangle, 1, 2, 3, and then there's a fourth one. Well, if you have a lot of triangles there, it pretty much needs to be a pyramid of some kind. The base is going to be this fourth figure right here. So that's the triangular base. And then faces 1, 2, and 3, those are going to be the lateral faces. Now, notice here, I've got 1, 2, 3, 4. I've got 4 rectangles. And then I've got 1, 2 squares. And so this right here is again, it kind of meets my pattern there. When you see a bunch of rectangles, it's probably good to go with a prism of some kind. And if we come down here to this pentagonal prism right here, notice I've got 2 bases that are pentagons, but then I've got 1, 2, 3, 4, 5 rectangles. And so my pattern is holding up there. And when you do the rest of these pyramids, typically with pyramids, you're going to see a ton of triangles, but there's going to be one shape that probably stands out, like a square. In this one here, there's my square that stands out right here. Or my hexagonal pyramid, here's my hexagon that'll kind of stand out. So you'll have one figure and then just a bunch of triangles if it's a pyramid. All right, the only oddball is the cone. This little circular region right here that I'm shading, This is the base of the that's the base of the figure. And this little fan region right here, this is the lateral part of the cone. And so that one's kind of a hard visualization. So just kind of, um, if we were in class, I'd be able to show you the what that looks like. We'd have something to kind of play with and look at. But for now, the best I can ask you to do is when you see something like that, a circle with a little fan type thing attached to it, just know that that's going to have to be a cone. All right, Dragons, that's it for section 12.1. Thank you all and be safe.